Okay, so let's start. So in the last couple of classes, we saw the capacity of a discrete memoryless channel with finite input and output alphabets, right? We showed that the capacity is equal to the maximum of the mutual information, where this maximum is taken over all possible input distribution speeds. And I briefly mentioned in the previous class that if you have a continuous input alphabet, then the capacity is the maximum of the mutual information, where this maximum is taken over all possible input densities, Fx. And it turns out that if you try to do this for an AWGN channel and you try to maximize over all possible input densities, then the capacity or the supremum of the mutual information between x and y turns out to be equal to infinity. And there's an intuitive reason for that, because if you have a certain level of noise, you can always increase the transmit power arbitrarily large, or you can increase the spacing between the transmitted symbols as much as you want until you have arbitrary reliability. But then in practice, you can't really do that, because if you wanted to do that, then the transmit power would essentially have to go to infinity, which is not reasonable in practice. So it means that there's something missing in our definition or understanding, or I guess in the formulation of the channel capacity problem itself. And that's because we have not taken into account the constraints that we may want to impose on the input, right? Because in practice, let's say when you're designing a communication system, you also have to operate under, let's say, power or intensity constraints, because that's always there in practice. So let's say that let's operate under the following setup, where we want to encode the message into a code word xn and transmit this through a channel. So the setup is still the same. We're operating with a discrete time channel, and we're transmitting over n time instants. The input and output alphabets can be arbitrary. So we'll distinguish between the cases where the input and output alphabets are finite versus the case where it is continuous. All right, so x and y, if these are finite or countably infinite, then the channel is specified by a conditional PMF, py given x. If these are uncountably infinite, or maybe I can distinguish between them being discrete versus then we'll assume that the channel is specified by a conditional density, Fy given x. All right. If there's no other constraint, then basically the capacity is the max max overall px of the mutual information between x and y. In the second case, the capacity is the maximum overall input densities of the mutual information between x and y. But now we'll impose some constraints on the input. You can't transmit any sequence xn, but there is some restriction on what kind of sequences can be sent through the channel. So you can have any number of input constraints, and we'll assume that the constraints are defined using some function. Let's call it phi I. So phi I is a function from the input alphabet to the set of reals, and you can have multiple input constraints potentially. Let's say there are L input constraints. Simplest case, there's only one input constraint. Okay. And the constraint is defined in the following way. We want 1 over n summation j equal to 1 to n of phi I of xj should be less than or equal to some quantity. Let's call it some rho I. The simplest case is where, let's say, phi of x is x square. Here the implicit assumption is that the input alphabet is the set of reals, and so this translates to an average power constraint. So basically, if you want to transmit something in n channel uses or n time instance, then you're only allowed to transmit sequences that satisfy this particular property. That 1 over n times summation xi j equal to 1 to n xj square should be less than or equal to p. Okay, so this is an average power constraint. P some number, which is specified at the time of designing the system. This is rho I because something more general, because this need not be a power constraint, it could be any cost constraint. So this is an average power constraint. Right? You could also have something like this. This is some P prime, which is sometimes called an average intensity constraint. You can define this. So if we have complex input alphabet, then you would require mod xj square. Okay. The assumption is that this function, whatever you define phi I, is from, if it's complex input alphabet, to the set of reals. Right? Because you can't really compare complex numbers. So it has to be a real valued function. Right, so for example, such constraints sometimes appear when you're looking at optical communication, where you don't just have power constraints, but you also have intensity constraints. So let's, in the context of, let's say, a BSC, binary symmetric channel, where the input alphabet is binary, sometimes you want to look at the following constraint. Basically, this says that the number of ones in the transmit sequence can be at most n times rho. All right, so this is sometimes called an average weight constraint. So it depends, depending on what kind of an application you have in mind, depending on what are the requirements on the system, you could have different types of constraints. But one thing to keep in mind is that all of the constraints are specified in this particular form. So in some sense it is restrictive, but it handles many of the constraints we see in practice. Okay. So under such a setting, you can show that the capacity with such input constraints is again given by the maximum of the mutual information between x and y. But now instead of taking the maximum over all possible input, just over all possible input distributions, we take the maximum over all possible input distributions px, or if it's a continuous input alphabet, then it's overall fx, such that the expectation of phi of x, where this expectation is taken using the distribution px, this is less than or equal to rho I for I equal to 1, 2, 3 up to L. So it has this nice form where it's again a maximum over the input distributions, but the input constraints also imposes a constraint on the distributions you are allowed to choose. And the way this appears in the capacity formulation, or the expression for the capacity, is that you maximize over all possible input distributions such that the expectation of phi of x is less than or equal to rho. All right. I won't formally prove this. It's not very hard to prove because essentially what you can do is you can follow the same steps of the achievability proof that we gave. The achievability is fairly simple. Essentially, you still take the typical set decoder. It's the same typical set decoder. Nothing changes at all. But the only thing that changes is the analysis of the probability of error. Now, again, if you recall the proof where we analyzed the probability of error, there were two types of errors. One, where this pair did not belong to the typical set, and the second, where there was some other code word which was jointly typical with this. The second part of the proof basically remains the same. The second bound remains the same, and you get essentially the same quantity. If you recall, the contribution of the second term to the probability of error was basically the 2 to the minus n times the mutual information. So that still appears, nothing else. The first part, in addition to the first part, there will be another error event, which is that you're randomly generating a code book. So the code word may not satisfy the cost constraint, the input constraint, because you're picking them at random, right? With some probability, if you pick a random sequence, it will not satisfy the constraint, say 1 over n summation xi square less than or equal to p. It may not satisfy the power constraint. So now there's a third error event, which is that what is the probability that the pair of that the generated code word, the randomly generated code word, does not satisfy the input constraint. But then again, using standard Chernoff bound, you can show that the probability of that happening is also very small. It's exponentially small. All right. So much of the proof remains essentially identical. There's only one additional step that appears in the proof. That's all. All right. And you end up with the same thing. You'll have the capacity being equal to a mutual information but except that now the maximization is over this restricted set of input distributions. All right. The non-trivial part is proving the converse, which requires a little more effort. All right. The achievability remains more or less the same. All right. So I won't derive this, but the reason why this is important is because in digital communications, the most common channel that you encounter is the AWGN channel. And typically it is the AWGN channel with a power constraint. So in this case, you have y equal to x plus z, where this z is assumed to be Gaussian with mean 0 and variance sigma square. So basically f of y given x is conditionally Gaussian, and it is Gaussian with mean x and variance sigma square. And there's a power constraint, which is that 1 over n times summation j equal to 1 to n xj square should be less than or equal to b. And for this channel, the capacity would be, again, the maximum over all possible input distributions, such that expectation x square is less than or equal to p of the mutual information between x and y. Question? This one here. So I'm talking about the density of y given x. So this is the density of z, right? So what is y? Y is basically z plus x. So the mean of y given x is equal to x. That's why y is Gaussian with mean x and variance sigma square. Any other questions? Okay. So the capacity is basically this mutual information, right? So we can try to evaluate what the maximum mutual information is. Let's look at I of xy. This is equal to the differential entropy of y minus the conditional differential entropy of y given x. What is the differential entropy of y given x? It's the differential entropy of z. And what is the differential entropy of z? Okay, anybody? What is the differential entropy of z? What is the differential entropy of a Gaussian with mean anything and variance sigma square? Your exam is on Sunday. So it's basically half log 2 pi e times the variance. All right. Now you can show that this, so let's look at the differential entropy of y. We've seen this a long time back. So firstly, what is the variance of y going to be equal to? Correct. So basically it's x and z are independent of each other. So the variance of y is basically equal to the variance of x plus variance of z. And we are saying that we're doing the maximization over all input densities for which the variance is less than or equal to p. All right. So this quantity is, let's say, expectation x square plus expectation z square, which is less than or equal to p plus sigma square, because expectation of x square is less than or equal to p. X is not necessarily, is not required to be zero mean, but you can still show that this holds. I mean, in any case, this is true. So basically what you can show is that the maximum is achieved when you take x to be zero mean. Z is zero mean, right? So it turns out that it doesn't really matter. So this quantity is less than or equal to p plus sigma square, right? So the variance of y is less than or equal to p plus sigma square. What is the maximum differential entropy of a continuous random variable with variance p plus sigma square? Or when is the differential entropy maximized? When it's a Gaussian, right? This was an exercise given to you some time back. So h of y is less than or equal to the differential entropy of a Gaussian with variance p plus sigma square. So this is less than or equal to half log 2 pi e times p plus sigma square. And this is achieved when you take h of y to be a Gaussian with variance p plus sigma square. Or equivalently, when you take x to be a Gaussian with variance sigma square, with mean 0 and variance sigma square, with mean 0 and variance p. Correct? Because if x is Gaussian with mean 0 and variance p, then y will be Gaussian with mean 0 and variance p plus sigma square. So the mutual information between x and y, no matter which input density you choose, is always going to be less than or equal to half log 2 pi e times p plus sigma square minus half log 2 pi e sigma square, and you have equality if and only if x is chosen to be Gaussian with variance with mean 0 and variance p. So this is equal to half log p plus sigma square divided by sigma square, which is just half log 1 plus p by sigma square. So the mutual information is always less than or equal to this particular quantity, and there is one particular density that achieves this particular mutual information. So the capacity of this channel is equal to half log 1 plus p by sigma square, and the capacity achieving input distribution is basically the Gaussian with mean 0 and variance p. I'm sorry? So it's achieved by this particular distribution. Right. In fact, you can see that if you take a mean which is not equal to 0, then expectation of x, what would expectation of x square be? So the variance is, okay, I did it a little quickly. Basically, variance of y is equal to variance of x plus variance of z. And the variance of, and we want the variance of y to be as large as possible. What can you say about the variance of x? It is expectation of x square minus expectation of x the whole square, right? And expectation x square is, it's at most p. So if you take the mean of x to be something non-zero, then the variance of x is only going to decrease, right? Which means that the variance of y would only be smaller. And the differential entropy is larger if the variance of y is larger. So that automatically sets the constraint that the ideal choice, the best choice, is to take x to have mean 0, and of course the variance has to be less than or equal to p. And the differential entropy is maximized when x is Gaussian. So the overall, so the capacity achieving input distribution is Gaussian with mean 0 and variance p. So the quantity p by sigma square is basically the ratio of the signal power p to the noise power sigma square. All right. So and this is called the signal to noise ratio. So this leads to the expression that some of you may be familiar with, that the capacity is basically half log 1 plus the signal to noise ratio. All right. So let's break this statement down a little bit. Let's try to understand what Shannon's channel coding theorem says. What the channel coding theorem says is that as long as you're transmitting at a rate which is less than half log 1 plus p by sigma square, as long as you choose a rate, you can find a sequence of codes, or effectively for large enough n, you can find a code for which the probability of error is decaying with n. Basically, it goes to 0 as n tends to infinity. And the rate is arbitrarily close to half log 1 plus p by sigma square. Okay. Let's look at this quantity half log 1 plus p by sigma square. When is this non-negative? Or when is it strictly positive? For what value?
1 plus p by sigma square is more than 1.
Correct. Or
SNR is positive.
as long as p by sigma square is positive. Or in other words, because sigma square is fixed by the channel, as long as p is greater than 0, you can transmit at a positive rate. All right? You can choose a large enough n. If you choose a large enough n, then you can transmit a positive fraction of information bits reliably through the channel, no matter how small p is relative to sigma square. Right? So even if p is 0.00001 times sigma square, this tells you that it's still possible to transmit at a positive rate, which is contrary to what people earlier believed, and also seems a little counterintuitive, because basically you're in a scenario where your signal power is much, much lower than the noise power. Even if it's so bad, even if the channel conditions are so bad, it is still possible to transmit at a positive rate. You can still get some reliable communication through this particular channel. The rate may be very small. Right? The rate is maybe like 0.001 bits per channel use. But if you take n large enough, let's say you take n to be a million, then it means that you can get roughly 1,000 useful information bits across this channel. So of course you're making this trade-off, that is you're increasing the delay by increasing n. But if you do that, it still means that you can communicate reliably through a channel where the conditions are extremely bad. The SNR is very, very low. Right? So as long as the SNR is positive, you can actually have reliable communication. And the price that you pay is in terms of the delay and complexity. But that's still a price that is still worth paying. Right? And that's a rather surprising observation. In hindsight, it seems okay, but at the time, this was considered a remarkable observation. All right. So let's look at some variants of this particular AWGN channel. In practice, if you've taken a course in digital communication, generally you fix the modulation alphabet. For example, if you know what it is, then you use either BPSK or QPSK or some kind of a modulation for transmission. All right. The simplest case is BPSK, where you're not allowing X to take any real number, but X is only allowed to take two values, some positive value or a negative value. And in this case, we'll take this to be either plus square root of P or minus square root of P. All right, that's a strong constraint. So now the channel is a bit different. The noise is still the same, but now you have an additional constraint on this particular input, that the input can't be any real number. It only can take values either plus square root of p or minus square root of p. Again, for this particular channel, the capacity is the same, right? So it's max overall possible input now x is discrete, so there are only two values this can take. You can find the maximum of the mutual information. Again, you know what py given x is or fy given x is. So this is an example of a channel where the input alphabet is finite, it takes only two values, but the output alphabet is infinite, it's the set of all reals. All right. So this is an example of what is called a constellation constrained AWGN channel. Because the noise is Gaussian, you are transmitting a symbol and the symbol is corrupted by additive noise, which is Gaussian. But now there's the constraint is that the input comes from some finite alphabet, which we'll call the constellation. Correct. So here the constraint is that the input comes from the BPSK constellation. More generally, we'll assume that the channel is a complex channel where you take the input alphabet to be the set of complex numbers, output alphabet to be complex numbers. The noise is complex AWGN, and the input comes from some finite subset of the complex numbers, which is the modulation alphabet. It could be either BPSK or QPSK or some PAM, 8 PAM or 8 QAM or any other such constellation. All right. Now it turns out even for this simple case where you have this BPSK input constraint, we don't have a closed form expression for the capacity. You can numerically evaluate this, but there is no closed form expression for the capacity. All right. But what can you say about this capacity in comparison to the capacity of just the normal AWGN channel with power constraint? Now, if you observe carefully, if you take x to take values either plus square root of p or minus square root of p, it still satisfies this power constraint that we had, right? Because each xj can take values either plus p or plus square root of p or minus square root of p. So in fact, this quantity is always exactly equal to p. All right. So what do you think? So if I call this C BPSK, what can you say about C BPSK versus C AWG?
AWGN is higher.
Okay, and why?
I'm maximizing over a larger set.
You are maximizing over a larger set, sure. Any other way of seeing this? Can you use an information inequality to show that this is actually, this capacity should be smaller?
Modulation, demodulation process can be thought of as a Markov chain.
Okay, very good.
And then you can use DPI to set that.
Correct. So basically you can say that, so basically you have x, which is in R, and you have the AWGN channel. standard AWGN channel where you get Y. Now you can think of an additional BPSK modulator which basically constrains the input x prime. So x prime can either take values 0 or 1. So this BPSK modulator essentially maps 0 to plus square root of p and 1 to minus square root of p, and then sends it across the normal AWGN channel, right? So in this case, you know that the mutual information between x prime and y, note that x prime x y now forms a Markov chain, because after all this BPSK modulation is essentially just a deterministic process. So by the data processing inequality, any additional form of processing can only decrease the mutual information. Right, so the capacity of the BPSK, the binary input AWGN channel, is less than or equal to the capacity of the standard AWGN channel. So this also highlights that if you do any other processing, right, let's say you fix a particular modulation scheme or add something specific, some algorithm at the decoder or at the encoder, then you're doing additional pre-processing or post-processing, which in the end will only reduce the capacity of the channel. Right? If you didn't have that specific, if you're allowed to design the algorithm without that specific pre-processing or that specific post-processing, then the capacity can only be higher. Now, in practice, you do add specific forms of pre-processing or post-processing mainly to reduce complexity constraints. All right? But if you didn't have these constraints, then the capacity could potentially be larger. Question? This is a form of pre-processing, yes. It still decreases the capacity. In fact, the capacity is much lower.
Post-process the output.
Correct.
That makes sense. Like the capacity is decreasing.
Correct.
Pre-processing.
I mean, it's the same logic, right? You're pre-processing, which is constraining the kind of inputs you're allowed to choose.
Why doesn't depend on stack?
Yeah, Y is still okay, but then your transmitted code words are now very, very restricted because they can only take two values, right? If you had the freedom to choose a larger set from a larger set, then potentially your capacity could be much higher. In specific regimes of SNR, this causes a significant hit. Because conditioned on X, right? What is Y? Y is just X plus Z, which is independent of X prime, right? So given X, you don't need to know anything about X prime to tell you what Y is. In this case, in this special case, it's far easier because there is a one-to-one mapping between X prime and X. But more generally, if this is any form of pre-processing, not just modulation, but you use any other potentially random pre-processing also, you will still only decrease the capacity.
CAWGN is the highest capacity.
the complex AWGN channel with just the power constraint has the. You need a power constraint, otherwise it will just be infinity. Right. So that with specific, if you impose a specific form of modulation, then the capacity is going to increase or decrease. Right. So, for example, let's say I have two different modulation alphabets. One is the BPSK, and the other is, say, 4PSK. Or so let's say you have BPSK, and the other is 4PAM. Basically, you're allowed to choose X from plus square root of P, minus square root of P, plus square root of P by 2, and minus square root of P by 2. Your modulation alphabet is now increased, and the modulation alphabet is a superset of the BPSK alphabet. For this, the capacity could potentially be higher than that of the BPSK constrained channel, because now you have more freedom in choosing the input distribution. Right? This, of course, increases the complexity of the transmitter. At the receiver, yeah, there is some increase in complexity because it mainly comes from how you decode. But then this could cause significant gain in the rate at which you can transmit.
Is it guaranteed that if I have a larger set, that I would get a better maximum?
It depends. It's definitely no worse, but at least in these examples, right? So BPSK versus say 4PAM versus just the AWGN channel, there is a strict improvement.
Okay, but it's definitely increasing, but not strictly.
No, it is strictly increasing.
Yeah, here.
In this case, yeah, but in general, it depends. It depends on the specific channel and the kind of input constraints you have. Any other questions? All right. So far what we've basically seen is communication systems or channel capacity where we assumed a discrete time model. Right? We're assuming that you're transmitting n symbols and the channel outputs n symbols. Right? But then if you zoom out of the communication system itself, what you're transmitting through the channel. If you go back to this, particular diagram of the typical digital communication system, if you go back to this model for the digital communication system, what is output? The output of this modulator or this modulation block is typically some kind of a continuous time waveform. All right, and the output of this physical channel is also a continuous time waveform. So when we were modeling this channel block, right, we assume that all of this part is fixed. That is, the modulator we used was fixed, and we were only allowed to design the channel coder and the channel encoder based on this assumption. Now you could naturally ask, suppose I also had freedom in designing the modulator block separately. Or to put it in other words, maybe I combine these two blocks together, the channel coding and the modulation blocks. So basically the input to the coding block would be a sequence of k bits, and the output is allowed to be a continuous time waveform. All right. Now basically I'm allowed to transmit for say t seconds, but within those t seconds I'm allowed to choose any continuous time signal. I can transmit any continuous time signal under some restrictions. Right? For example, the power has to be constrained, or the energy has to be constrained, and potentially some other potentially, usually the bandwidth also has to be constrained. All right. Now, for such a system, so the setup we have is the following. You are given a sequence of k message bits as input. The output is a signal x of t for t from 0 to some capital T. All right. And the output is again a continuous time signal which is fed to a decoder which outputs an estimate of the message. And the standard, the most relevant channel that one typically looks at is this band limited AWGN channel, where you're only allowed to transmit within a frequency band of bandwidth W. And you have an input constraint where the power spectral density of x of t is at most p, and the power spectral, again it's an AWGN channel, so y of t is equal to x of t plus some z of t. Where z of t is a Gaussian process with power spectral density, say sigma square. All right. Now, under this constraint, one can try to find the capacity of the channel. And here again, it turns out that the capacity, now this requires a lot more complicated mathematical formulation. Because now the input is no longer a nice, simple, finite dimensional vector space. All right. So, but what you can show is that the capacity of this channel is W log 1 plus the signal to noise ratio, which is something that you would see in a textbook on digital communications. All right. So basically, if a lot of digital communication textbooks just use this formula for the capacity of the band limited AWGN channel. Again, it's not an easy task. It is the derivation isn't as simple as the derivation that we did for discrete time channels. But one thing to be kept in mind is that the capacity of this particular channel is potentially larger than the capacity of the corresponding discrete time channel by assuming a specific form of discretization. Right? because in the end you're doing some form of pre-processing and post-processing in order to get that specific discrete time AWGN channel. So in a sense, this W log 1 plus SNR is the theoretical maximum rate at which you can possibly transmit through the channel. But in practice, you are a bit away from this particular capacity. You don't really hit this capacity because in general, you have a lot of additional constraints. For one, you have this discretization in time. And secondly, you typically also have a constraint on the modulation alphabet that you use. Because in practice, you use either some form of PSK or PAM or QAM. Right? All of these restrict the capacity. So even though this is theoretically the maximum rate at which you can transmit, in practice, you are far away from this. All right? Any questions? All right. So again, in this course, we've kind of just scratched the surface of information theory and what can be seen. And pretty much everything that we have seen so far is what is sometimes called point-to-point information theory. That is, there's one transmitter and one receiver. When you are doing compression, there is one file to be compressed and one person who wants to reconstruct the compressed file. When you're talking about channel coding, there's one single transmitter and one single receiver. But a lot of this can be expanded. Similar ideas can be used to also study multi-terminal systems. Right? For example, in a practical communication system, you have not just one transmitter and one receiver, but you have multiple transmitters and multiple receivers. Or let's say you're communicating to a single base station, there are multiple users who are communicating to a single base station. Right? So you have transmitter 1, transmitter 2, say K transmitters, who are all communicating to a single base station, which is one receiver. So this is an example of a multiple input, multiple transmitters, but single receiver. And this is what happens in the so-called uplink of the communication system. That is, the cell phones are talking to the base station. And this is an example of a multiple access channel. All right, sometimes abbreviated as a MAC. And in the downlink, when the base station is sending messages to the individual users, you have the reverse. You have a single transmitter, but potentially multiple receivers. And this is called the broadcast channel. So a simple example of a multiple access channel is, let's say that user 1 sends x1, user 2 sends x2, user k sends xk, then the receiver gets x1 plus x2 plus x3 and so on, plus some additive noise. That's a simple Gaussian multiple access channel. And similarly, if for the broadcast channel on the downlink, the simplest model is, let's say transmitter sends x, then receiver 1 gets x plus z1, receiver 2 gets x plus z2, and so on. Right? So that's an example of a broadcast channel. Now the complications arise because, let's say in the multiple access channel, each of these users is sending the same, sending their own messages which are independent of each other, and the receiver has to reconstruct all of those messages. So there's a lot of interference in this particular channel. All right? And in the broadcast channel, the transmitter has messages. It has one message for receiver 1, a different message for receiver 2, and so on. It's not the same message that is being broadcasted to everyone. There's a separate message which is intended for receiver 1. There's a separate message which is intended for receiver 2, and so on. Sometimes there can also be common messages, right? But there can also be independent messages for different receivers. So under all of these, one can ask what is the maximum rate or best rates at which you can transmit, for which you can reliably reconstruct, the receiver can reliably reconstruct the individual respective messages. All right? And this has been well studied. When you look at the channel itself, it may seem as though the multiple access channel is harder to study than the broadcast channel, because in this case you have interference to take care of. All right? So conceptually, it seems like the multiple access channel is harder, but it turns out that the so-called capacity, in this case it's not really one capacity, but rather a capacity region. The capacity of the multiple access channel is fairly well understood. You can find out what is the best set of best rates that you can achieve. In contrast, the capacity region of the broadcast channel is unknown. It's still an open problem for several decades now. All right. And a more general model is where you have multiple transmitters and multiple receivers. And this is what is called an interference channel. So these are common channels in the context of channel coding, studied under the broad umbrella of multi-terminal information theory. Many of these ideas, particularly related to the multiple access channel and the broadcast channel, have seen some form of resurgence in recent years under the name non-orthogonal multiple access. It's a bit of a misnomer, but that term has stuck. But a lot of the results essentially are drawn from known results on multiple access channels and broadcast channels. All right. So if you want to learn more about these multi-terminal information theory in general, there is a chapter in Cover and Thomas on network information theory or multi-terminal information theory. But then if you're, but a better reference, maybe a more up-to-date reference, is the book by L. Gamal and Kim, which talks about this in a lot more detail. All right. Particularly if you are interested in working, let's say, on wireless communications and something like non-orthogonal multiple access technologies, I think this is a very valuable resource to go through, because many of the foundational ideas basically comes from these ideas themselves. Just as you have this multi-terminal channel coding, one can also talk about multi-terminal source coding, where you again have multiple transmitters where you generally have correlated files, and the goal is to compress each of these individually to using as few bits as possible, such that the receiver can reconstruct it. There are a number of other channel and source models that are also studied in the literature, and this book has essentially covers many of these problems in a lot of detail. Okay, so I guess that's basically what I wanted to cover in this particular course. If you want to explore more of channel coding, there will be other courses offered in the upcoming semesters. For example, the coding theory or error correcting codes course will talk about how do you design channel codes for specific channels. All right, where the focus will be more on algorithmic aspects. How do you design an efficient channel code? How do you design a capacity achieving channel code? Where typically you restrict yourself to only binary channels. So it seems like a restriction, but even that problem is not easy. All right, and something else that we have never covered in this course is quantum systems. So let's say that you have a quantum channel or a quantum source, whatever that means. Again, what do you mean by compression in that particular context? How do you communicate reliably in such a scenario? And what are the fundamental limits of communication or compression in such a scenario? Right, so that's covered broadly under quantum information theory. Okay, so I guess we'll stop here.